Welcome to AI Frontiers. In this episode, the focus is a comprehensive synthesis of the most recent advancements in robotics research, specifically highlighting 15 influential papers published under the robotics category of computer science, designated as cs.RO, in May 2025. This deep dive explores foundational concepts in robotics, the central research themes emerging from the latest literature, and the methods that are propelling the field forward. The narrative spans a wide array of topics, including perception, learning, safety, and autonomy, and aims to provide an accessible yet technically rich perspective for robotics enthusiasts, researchers, and those intrigued by the intersection of artificial intelligence and physical machines. Key breakthroughs, seminal works, and the broader impacts of these studies will be discussed, painting a detailed picture of the state of the art in robotics and its significance for both industry and society. To establish context, robotics as defined within computer science, under the cs.RO classification, is an inherently interdisciplinary field. It integrates principles from artificial intelligence, mechanical engineering, electrical engineering, and human-computer interaction. This domain focuses on endowing machines with the capability to sense their environment, make autonomous decisions, and act effectively. Robots manifest in various forms, from self-driving cars traversing urban landscapes, drones performing aerial reconnaissance, industrial robots assembling products, to domestic robots assisting in homes. The societal and industrial impact of robotics is profound. Healthcare is being transformed through robotic surgery and assistive technologies. Transportation is rapidly evolving with automated driving systems. Manufacturing is achieving new levels of precision and efficiency through industrial automation. Logistics and delivery are becoming more agile with mobile robots. And even everyday life is being reshaped by the introduction of robotic companions. Central to the field are advances in perception, control, learning, and interactive capabilities, all of which are driving the expansion and integration of robotics across domains. A dominant theme in current robotics research is autonomous perception and decision-making, critical for robots operating in complex, real-world environments. Robots must continuously interpret their surroundings and make decisions that ensure both safety and efficiency while achieving their assigned objectives. The research paper titled, DriveSOTIF, Advancing Perception SOTIF through Multimodal Large Language Models, authored by Huang and colleagues, exemplifies the integration of visual and textual modalities to enhance context-aware decision-making in autonomous vehicles. Similarly, the work known as VoliSense demonstrates how sensor fusion, combining data from lidar, radar, and cameras, enables connected vehicles to achieve richer and more robust situational awareness. These innovations in multimodal perception are instrumental in improving risk assessment and are essential for achieving reliable autonomy in dynamic traffic and operational scenarios. Another major research theme centers on teaching robots through demonstration and imitation, bypassing the need for exhaustive explicit programming. Instead of coding every possible behavior, robots are being enabled to learn complex skills directly from human demonstrations. The paper, arXiv, Cross-Embodiment Learning via Real-to-Sim-to-Real, authored by Dan and collaborators, introduces a pipeline in which robots acquire manipulation skills from videos of humans performing tasks. This approach minimizes the requirement for robot-specific action data and teleoperation, facilitating the transfer of skills across different robotic embodiments. The result is a scalable, data-efficient framework that supports the acquisition of a diverse set of tasks, marking a significant step toward versatile and adaptable robotic systems. Safety, robust control, and explainability have emerged as critical priorities in advancing trustworthy robotic behavior. The research by Tan and colleagues, presented in Secure Safety Filter, Towards Safe Flight Control Under Sensor Attacks, addresses the resilience of drones operating under compromised sensor conditions. Additional work on dynamic safety filters explores methods for guaranteeing safe actions in environments characterized by uncertainty and change. Explainability is also gaining prominence, as techniques such as counterfactual reasoning are employed to clarify the rationale behind robot decisions. Fast-slow architectures, which integrate user guidance with machine learning, further enhance transparency and user trust. Collectively, these efforts underscore the growing importance of safety and transparency as robotics systems are deployed in safety-critical and human-centric contexts. Efficient planning and real-time operation represent another crucial area of focus for modern robotics. Robots are increasingly required to perform rapid planning and decision-making to function effectively in dynamic and often unpredictable environments. The cs.RO framework leverages the computational power of graphics processing units to accelerate motion planning, enabling robots to identify feasible and safe trajectories with remarkable speed. Approaches such as latent space planning are being developed to address high-dimensional, constraint-rich scenarios, ensuring scalability and practical deployment. These real-time algorithms are essential for the integration of robotic solutions in industry and everyday life, supporting applications that demand both precision and immediate responsiveness. Several key findings have emerged from the synthesis of the May 2025 robotics research papers. First, the scalability of real-to-sim-to-real learning has been empirically validated, as demonstrated by Dan and colleagues. Second, robust safety filters capable of detecting and mitigating sensor attacks, exemplified by the work of Tan et al., are proving vital for the deployment of trustworthy autonomous systems. Third, the integration of multimodal large language models into perception systems, as illustrated by Huang et al., is enhancing the safety of the intended functionality, or SOTIF, in autonomous vehicles. Additionally, GPU-accelerated planning methodologies are unlocking real-time operational capabilities for sophisticated robotic systems. Finally, the growing emphasis on explainability is bridging the gap between human and robot understanding, facilitating greater transparency and trust in autonomous decision-making. A range of core methodologies is propelling advancements in robotics. Deep reinforcement learning enables robots to develop adaptive control policies through interaction with their environments, excelling in high-dimensional, continuous domains. Sensor fusion techniques combine data from multiple modalities, including lidar, radar, and cameras, to provide comprehensive and robust perception, though challenges in calibration and synchronization persist. Simulation-to-real transfer, commonly referred to as sim-to-real, allows for the development and refinement of robot policies in virtual environments before deployment in the real world. Explainable artificial intelligence methodologies, such as the generation of counterfactual scenarios, are being implemented to make robot reasoning more transparent. Meanwhile, the field continues to debate the merits of modular versus end-to-end system architectures, with approaches like YAPOV2 Tracker exemplifying the balance between flexibility, performance, and interpretability. A closer examination of the seminal paper, arXiv, Cross-Embodiment Learning via Real-to-Sim-to-Real, authored by Prithvish Dan and colleagues in 2025, reveals a novel approach to robot skill acquisition. This work addresses the challenge of teaching robots complex manipulation tasks solely from human demonstration videos, eliminating the need for direct robot action data or teleoperation. The arXiv framework employs a multi-stage process, beginning with the reconstruction of photorealistic simulations from RGBD videos of human demonstrations. Object-centric rewards are used to guide policy learning in simulation, after which the trained policy is distilled into an image-conditioned diffusion policy. Synthetic rollouts with diverse camera viewpoints and lighting conditions support generalization. For real-world deployment, online domain adaptation aligns sensory observations between simulation and reality. Empirical results across multiple tasks and environments indicate a 30% improvement in task progress compared to prior methods, with a tenfold reduction in data collection time relative to behavior cloning. The framework generalizes effectively to novel viewpoints and changing environmental conditions, highlighting the scalability and efficiency of this embodiment-agnostic approach. The second influential paper, DriveSOTIF, Advancing Perception SOTIF through Multimodal Large Language Models, authored by Shucheng Huang and colleagues in 2025, confronts the challenge of ensuring the safety of the intended functionality, SOTIF, in autonomous vehicles. This work leverages multimodal large language models, capable of processing both visual and textual information, to address complex driving scenarios where traditional systems may falter. A custom dataset capturing real-world driving hazards is used to fine-tune these models, enabling enhanced context-aware and real-time decision-making. Comparative analyses against standard benchmarks reveal that the models outperform conventional systems in safety-critical situations, demonstrating more reliable and faster responses. The integration of these multimodal models brings human-like reasoning capabilities to autonomous vehicles, underscoring the potential for improved safety and increased public trust in automated driving technologies. The third seminal paper, Secure Safety Filter, Towards Safe Flight Control Under Sensor Attacks, authored by Xiao Tan and colleagues in 2025, addresses the vulnerability of autonomous drones to sensor failures or adversarial attacks. The secure safety filter comprises two primary components: a secure state reconstructor, which estimates the most plausible system state when sensor data are compromised, and a safety filter, which determines the safest control actions while maintaining proximity to the desired trajectory. This system is designed to accommodate nonlinear dynamics and measurement noise, surpassing prior methods that often assume linearity or ideal conditions. Validation in both software simulations and real drone hardware confirms the filter's ability to maintain safe operation under attack conditions that would otherwise cause conventional controllers to fail. The modular nature of the secure safety filter facilitates integration with existing autopilot systems, representing a significant advancement in the reliability and practical safety of autonomous aerial vehicles. Looking ahead, several future directions and challenges have been identified from the current trajectory of robotics research. Improving simulation to real transfer, particularly for highly dynamic and complex environments, remains an open problem. Strengthening explainability and human alignment is increasingly vital, as robots are expected to interact more closely with people in diverse contexts. Scaling data collection to support broader skill acquisition is another key concern, as is enhancing computational efficiency to meet the demands of real-time applications. Above all, ensuring safety and fostering trust are paramount as robots continue to transition from controlled laboratory settings into the fabric of daily life, underscoring the need for ongoing innovation and responsible system design. A technical spotlight on deep reinforcement learning and sensor fusion reveals their foundational roles in contemporary robotics. Deep reinforcement learning enables robots to refine their behaviors through iterative environmental feedback, allowing for the emergence of robust and adaptive control strategies. Sensor fusion, achieved by merging data streams from lidar, radar, and cameras, delivers a comprehensive perception of the environment, facilitating effective navigation and task execution. The synergy of these techniques underpins significant advances in both perception and control, as illustrated in the works of Dan et al., Huang et al., and Tan et al. Their contributions demonstrate how these core methodologies are central to the development of versatile and resilient robotic systems. Another technical spotlight focuses on explainable artificial intelligence and simulation to real transfer, two pillars supporting the trustworthiness and adaptability of modern robots. Explainable AI methods, such as counterfactual explanations, enhance transparency by clarifying the reasoning behind robotic actions, thereby fostering user trust. Simulation to real, or sim to real, strategies involve training robots in virtual environments before adapting them to real-world conditions, which reduces both risk and the time required for learning new tasks. These approaches are essential for achieving scalable and reliable robotic autonomy and are prominently featured in the XSIM framework by Dan et al. and the DriveSOTIF system by Huang et al., both of which highlight the critical importance of adaptability and transparency in autonomous systems. The synthesis and review process for this presentation utilized state-of-the-art artificial intelligence tools and expert oversight. Textual analysis and narrative development were conducted using GPT-4.1 by OpenAI, ensuring comprehensive coverage and technical accuracy. Voice synthesis was accomplished with Google TTS, while Grok supported the creation of visual illustrations. Human experts reviewed the summaries to further enhance clarity and reliability, though minor oversights may persist. All relevant references are included to ensure transparency. This collaborative approach between AI and human experts guarantees a thorough and reliable synthesis of the robotics research landscape. Thank you for joining this exploration of robotics research on AI Frontiers. For continued insights into the latest developments in artificial intelligence and robotics, Subscribing ensures access to future episodes featuring groundbreaking research and emerging trends. AI Frontiers is committed to delivering comprehensive research synthesis and analysis, making advanced topics in computer science and robotics accessible to a broad audience. Your engagement, through likes, comments, and shares, supports the mission of fostering understanding and innovation in these rapidly evolving fields. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.